In this video, I'm going to go over several examples, both how to go from a name to a formula or how to go from a formula to a name. So let's just start at the top. So this is an acid, right? I mean, it says acid there. Now, what I got to be careful of is that this starts with hypo. We never saw anything that started with hypo except for hypobromite. Now here's where it comes in with the acid naming. Remember that acids that end with ite get an us. So what this is HBRO. Hydrobromic acid, on the other hand, would be HBr. And we'll add AQ on here just so that I can be proper. Okay, now magnesium, and now I have selenate. So I grab my periodic table, and when I look, I see that selenium is in the same row as sulfur. So since they're in, or excuse me, the same column. So since that's true, basically what happened here is I took sulfate, right, 8, and I replaced the sulfur with selenium. So this has a -2, magnesium has a +2, this is Se4. Mercury 1 chloride, okay? So remember that mercury 1 looks like this, and it has a +2 charge, Cl2. Now, this is very much like hydrogen peroxide or sodium peroxide. We cannot reduce this because effectively what I have going on with mercury is something like this. Each one of these guys has a +1 oxidation state. Let's see here. Zinc oxide, that one's pretty easy. That's just a regular old ionic compound. Good. Zinc only has 1 oxidation state. It's +2. Chromic acid. All right, so we relate ic, right? So if we have 8, we replace it with ic. So that is chromate. Chromate is CrO4 2-. Now, I need the proper number of hydrogens to kind of balance this out, and so this becomes H2CrO4. Remember, none of these compounds should have a charge once we're all said and done. Okay? And I'll add the AQ on there just to be safe. Silver acetate, pretty easy, AgC2H3O2. Stannous fluoride. Okay, stannous is tin 2. So that's a +2, means I need 2 fluorines to balance it out. Sodium dichromate. So I have Na. I'm going to need 2 of them because each one has a +1 charge. And my dichromate is Cr2O7. -2 charge, balanced out with the +2 from the sodiums. Cupric nitrate. Remember, you have us and ic. So ic on copper is the +2. So that makes this Cu, and then I need to use parentheses around the nitrates because remember, these are whole groups. You do not distribute that 2. Uranium 6 oxide. So I have uranium, it has a +6. I need oxygen, has a -2. That means I need 3 of these guys, and so this becomes UO3. Barium hydroxide, fairly easy, barium, and I have 2 hydroxides, not to be confused with barium hydride. Barium hydride would be BaH2. Hydride, not to be confused with hydrates, are where I have hydrogen acting as an anion. Lithium bisulfite, so I have lithium bisulfite, looks like, almost put it 4, it's a 3. There we go. Cool, I got a binary molecular compound. So this is N2O5. Acetic acid is vinegar. It's acetate, right? We have the ic. We drop the ic and put the 8 back on. Balance out the hydrogens. Thiosulfuric acid. So this one's a fun one. All right, I'm going to start putting these down below now. Okay, so P. All right, so we know we have sulfuric, right, which is SO4 2-. But the problem is we have thio on the front. Remember, with thio, we drop an oxygen and add +1 sulfur. So the anion looks like this. Then to get the acid, I need to add the proper number of hydrogens. And I'm going to add AQ back up here for acetic acid. H2, S2, 3, AQ. Hydrocyanic acid. So I had the hydro portion with an ic. Hydroic means it ended with 8. or excuse me, ide. Cyanide is like that. So this is, I need to balance out the charge with a hydrogen and a Q. Hydrogen sulfide, H2S. And cadmium permanganate. Cadmium only has one oxidation state. And this is MnO4 2. Alright, now we're going to go the other way. Starting with the metal, going to be doing ionic naming. Doesn't have hydrate on it. This is my anion, that's bicarbonate, or hydrogen carbonate if you'd like. This is sodium bicarbonate, or baking soda. Let's see here, I have ammonium, starts with ammonium, right? So we use the ionic, doesn't have the hydrates on the end. Ammonium phosphite. Starts with the metal, doesn't have hydrate on it. So this is potassium sulfate. Okay, now I have iron here. Okay, remember iron has multiple oxidation states. So the first thing I'm going to do is I'm going to identify what my anion is. It's hypochlorite. Hypochlorite has a -1 charge, and I have 2 of them, meaning that iron has to have a +2 charge, and there's only one of them. So here I'm dealing with iron 2 hypochlorite, or ferrous hypochlorite. I don't know what that weird bit out here is. Get rid of it. There we go. Okay, start with a metal, but I have the hydrate at the end. So this is, let's see here. Oh, this is nice because it also has different oxidation states. So we have manganese 2, not to be confused with magnesium, bromide, and it's a hydrate, so I have to tell how many there are. This is tetrahydrate. Or I could have this be manganous. Oops, shouldn't be any on there. Sorry. Yes. Go. Next, I have gallium. Where's gallium on the periodic table? Let's take a quick look at that. I believe this is one of those that has, yes, could possibly have more than one oxidation state. In this case, we have oxygen, which is going to have a -2. That's -6 on the left-hand side. That means I have to have a +6, -6 on the right-hand side. I need to have a +6 on the left-hand side. That means each one of these galliums is 3. Therefore, this is gallium 1, 2, 3 oxide. All right, I'm going to be angling down here a little bit. So here is pretty easy, ammonia. Not ammonium, ammonia. Here, I have a binary molecular covalent compound. So this is tri-phosphorus. Excuse me, let me back up just a second. I always do this. Phosphorus. Oh, I want an eraser, not that. There we go. Ah! Go away. There we go. Triphosphorus. And I have 7 of them, so that's heptachloride. Next, I have HI as an acid, so this is hydroiodic acid, right? Because it's iodide, we dropped the ide and we had an hydro hit to it. Okay, so for some of these, I'm going to start moving over on the other side. This does not have the AQ with it, so this is hydrogen fluoride. This is sulfurous acid. This is bromic acid. Calcium oxalate. No Roman numerals. Calcium only has one oxidation state that it'll take. Vanadium has multiple oxidation states, so this is vanadium vanadium 4 chloride. Notice no Greek prefixes. Ooh, this one's interesting. Okay, so we got copper here. This has multiple oxidation states. We have arsenic, where, oh, I've never seen that before. If you ever think that, go back and check and see where it's attached to, right, or what group it's in. Arsenic is in the same group as phosphorus. Okay, so that means I'm going to name this like phosphate, and it's going to have a -3 charge. But I add a hydrogen onto there, so that bumps it down by 1. So here, copper has to have a +2 oxidation state in order to balance out the charge. So this becomes cupric, or copper 2, hydrogen, arsenate. This is carbonic acid, strontium. What do you think? Strontium oxide, right? No. Remember that strontium has a +2, right? So that means that this whole thing has to have a -2, but I have 2 of them. So this is strontium peroxide. Very common mistake. Let's see here. I'll do this one over here. I have rubidium nitrite. And finally, this is my favorite acid to name. It's periodic acid, but it looks like periodic. That's fun. So, in general, we can kind of classify ionic compounds and molecular compounds based on their properties. Not almost. Every single ionic compound is a crystal solid at room temperature, whereas molecular compounds could be all kinds of different stuff. Generally, ionics are hard and brittle. Think about like table salt. Whereas molecular compounds have a wide range of properties. These guys generally have high melting points and high boiling points, whereas many molecular compounds have low melting, low boiling points. For example, think of all the gases on the right-hand side of the periodic table, right? Oxygen, fluorine, chlorine, nitrogen are all gases at room temperature. Ionic compounds will break apart sometimes. Many of them will. Sometimes just a little bit to form electrolytes in solution. Generally, molecular compounds don't, although we're going to see that there is these ones that form kind of weak electrolytes. And ionic compounds have strong or decent electronegativity. Sorry, let me back up. Electron conductivity, very different, whenever they're molten. In other words, whenever they're a liquid, versus molecular compounds do not. This is a way we can kind of classify these things. So these are the examples. You have a lot of practice that you can do. I provide answer sheets so you can check your answers. So you definitely need to go and you need to work through this and figure these things out and try them out. Okay, it takes practice, and the only way you stay good at this stuff is to continue to practice it.